Alright, so unfortunately today our normal method of my recording the lecture didn't work out so well, but I've got an improved virtual whiteboard here, so I'm going to review the magnesium oxide example that we did in class so that if you missed that, you can see it again. Alright, so what did we start with? Okay, so we were working on the same exact experiment you guys did in class, where you had some magnesium metal, pure magnesium, and you burned it. And so you had oxygen gas coming in from the atmosphere, and when you combine those two things, you end up generating magnesium oxide. Now that is a locked-in thing that actually happens. Pure magnesium plus oxygen gas from the atmosphere is going to give you magnesium oxide made of 1 magnesium and 1 oxygen. All right, so undo those. You can't change the formula of magnesium oxide. So we talked in class about how carbon monoxide and carbon dioxide are two completely different substances. And one, if it leaks into your house, can kill you and your kids and your dog and everybody. And carbon dioxide is in your body right now and you're breathing it out and it's not a big deal. So you can't start messing around putting little 2s and 3s next to things. So the problem we have there, take care of that. When we look at this situation, we know that magnesium plus O2 gas is going to give you magnesium oxide, and magnesium oxide has to specifically be made of 1 magnesium and 1 oxygen. That's guaranteed. But we also know that a reaction has to be balanced. So everything that appears over here on the left side has to show up over here on the right side. So if we do a tally right now, over here on the left side, we've got 1 magnesium, because that's this guy right here. And then when we look at this O2 that we've got here, that means that there's 2 oxygen atoms stuck together. So that means if we're tallying up how many oxygen atoms are over on the left, we're going to have 2 oxygens over there, all right? So let me just take care of that. So 2 oxygens over on the left side. Over on the right side, we've got this 1 magnesium, and then the other part of magnesium oxide is 1 oxygen. So we have a problem here. These two, great, matched up. These two, not good, because we've got 2 oxygens on the left side and only 1 oxygen on the right side. So we have a situation here that we have to try to fix. Now, because we can't mess with the formula, so magnesium oxide has to be MgO. That's what magnesium oxide is. Carbon dioxide is CO2, carbon monoxide is CO. So we can't just change the number of oxygens here. We can't just do this. Now, if we did that, it would solve our problem, because then we'd have 2 oxygens here, 2 oxygens on the left, 1 magnesium on each side, everything's great. But that's not going to fly, because magnesium oxide is what it is. 1 magnesium, 1 oxygen stuck together. That's the nature of the beast. So we have to find a way to fix this up so that our equation is balanced. Now, as we talked about in class, the way we can do that is we can't just stick numbers next to individual parts of a formula, so we can't be, sticking 2s in here and changing things in there. But what we can do is we can change how many of these things we have. We could have 2 magnesium oxides, or 3, or 71, whatever we want. So we can change that part. So in class, we looked at what happens if you put a 2 here. So we're saying 2 magnesium oxides over on the right side of our equation. Now if we come down here, and we look at our retallied situation, if we have 2, oops, that's not what I meant to do. If we have 2 magnesium oxides, so this is the whole unit. So we've got magnesium oxide as the unit, and we've got 2 of them. That means we have 2 of every part of this magnesium oxide. That means there's 2 of them and 2 of the oxygen part as well. So if we do that, take this box away, and we do our retally, now based on this, we have 2 magnesiums, and we also have 2 of the oxygens. So now we've got a situation where the oxygen is all set. There's 2 on the left and 2 on the right. But the magnesium is not all set, because we've got 1 magnesium on the left and 2 magnesiums on the right. So the solution we came up with in class was to say, all right, what if we put a 2 over here? And then when we retally, we see we've got 2 magnesiums on the left, 2 oxygens on the left, because we have this O2 here. And then over on the right, we had already figured out that we had 2 magnesiums and also 2 oxygens. So now set up the way it is, everything checks out. So at this point, we've balanced our equation. That's good news. So we'll take that stuff away. And I'll erase this stuff. So, oops, I unbalanced the equation. I got a little overzealous with my eraser undo function. So we have 2 magnesium plus O2 gives us 2 magnesium oxide. That's a balanced equation. Everything's great. So what that is telling you is every time you run this reaction, for every 2 magnesiums you put into it, you're only going to need 1 molecule of O2, because the way we read these reactions is if there's nothing, no number in front of something, it defaults to a 1. So 2 magnesiums plus 1 molecule of O2 are going to give you 2 magnesium oxides. That's what this reaction is telling you. That is locked in. So this thing needs to clear. Change colors. Ooh, fabulous. Okay. So now what we have to do is we have to use this reaction to try to make some predictions. So what you were given in class is that we started out with, ooh, that's terrible. We started out in class with 1.89 grams of magnesium. And the question is, how many grams of magnesium oxide will that give us if we run this reaction where we burn it in a crucible and oxygen comes in and they combine and all that, yada, yada. But the problem that we ran into is that you can't use this reaction to get you directly from a grams amount to another grams amount. So this reaction that we're looking at doesn't work that way. So that means you can't go directly from grams to grams. So what we're going to have to do is we're going to have to convert this. We're going to have to take this grams and put it into some sort of currency that our equation can work with. So if we look here, the way to think about this is you think about this balanced reaction that you worked so hard to make, and I'm going to just clear out some of this stuff, make it a little easier to see what's going on. What we've done here is you've made a machine. You've made a machine that can predict what's going to come out one end of the equation if you put something in the other end. Now the problem is what's in this box, this machine that you've built, only accepts a certain kind of currency. It can only tell you how many of something is going to be generated. So what it's telling you is if you have 2 magnesiums that you put in on the left side, it's going to kick out 2 magnesiums over on the right side. So that ratio is locked in, 2 magnesium to 2 magnesium oxide. Now we can simplify that ratio into 1 magnesium to 1 magnesium oxide. So what this is saying is no matter how many magnesiums you put in on the left, you should get the same number of magnesium oxides out on the right side. But we can't go directly to using that machine with grams because these 2's are not talking about grams. It's not saying 2 grams of magnesium will give you 2 grams of magnesium oxide. That doesn't make any sense because 2 grams of magnesium is being combined with some amount of oxygen and it's going to give you this. So this magnesium oxide over on the right is going to be heavier than your original magnesium because you've added oxygen. So we can't go directly from grams to grams. We're going to have to get this into something that this machine in the box accepts. And the machine in the box can only talk to you about how many of something is going to be generated based on the number of something else that you put in. So the ratio is locked in. For every 1 magnesium you put in on the left, you're going to generate 1 magnesium oxide over on the right. So the question is, if we've got this number, 1.89 grams of magnesium, and we want to try to figure out how many grams of magnesium oxide are going to come out over on the right side, we have to convert our grams number into something that our machine can accept. So what we're going to do there is we're going to convert into moles. So we'll take that, we'll take our grams and we'll convert it into moles because moles is a number of something. And our equation only speaks about numbers of things. So we have to get our grams into moles in order to be able to use our number machine up here at the top. So what we need to do here is we'll clear away some of this stuff, make ourselves a little space. We're going to convert to moles. All right. So what we determined, and we'll go back to this, we determined that we have to somehow have some sort of conversion factor that's going to take us from 1.89 grams of magnesium, and it's going to get us into moles of magnesium, right? So we're going to have some conversion factor here that's going to get us there. So we know that if we're trying to get rid of grams, grams better be on the bottom, and moles better be on the top, because that way moles will stay, grams will go away, and then we have something we can work with. So we have to find out, what does 1 mole of magnesium weigh? Well, luckily you can go to your periodic table and you're going to look and find out that that's how much a mole of magnesium weighs. So 1 mole is equal to 24.305 grams for magnesium, and then you're going to plug this into your calculator, and it's going to give you some number, which I think I remember from class was 0.07776 moles of magnesium. So that's great. So now you know how many moles of magnesium need to go into Now you know how many moles of magnesium are going into the machine. So you already knew how many grams were going into the machine, but the machine couldn't accept grams. It couldn't do anything with the information about grams. So now, let me erase this. We've now converted this grams number into a number of moles. And that's usable by the machine. So the machine accepts moles. It knows how to deal with moles. Because this machine in our red box up here is telling you that however many moles you put in over on this side, you're going to get the same number of moles out the other side. So that means that once you have this number of moles of magnesium, your machine is telling you that you're going to have the same number of moles of magnesium oxide coming out the other end. So that means we know that we should, in a perfect world where the experiment goes 100% the way it's supposed to, we should get 0.07776 moles of magnesium oxide out, since that's the number of moles we put in, and our ratio is telling us it's 1 to 1, 1 to 1 all the time. So now we know how many moles of this magnesium oxide should come out the right side, but we're trying to find out how many grams that would be. So that means another conversion. So it's going to feel like you're just going around in circles. That's normal. And that's what you have to do. There's no other way. Because if you want to use this machine up here, you have to give it moles to work with. But you're generally in the lab going to be working with grams. And your answers are going to be requested in grams. So you got to convert to moles, run it through the machine, and then convert back to grams. So if we're going to convert back to grams, we're going to take our 0.0776 moles, and this time it's of magnesium oxide. So we're going to do our conversion, and this is going to give us grams of magnesium oxide. So now we want moles to go away. So now moles is going to need to be on the bottom, grams on the top, moles goes away, and we have to figure out what 1 mole of magnesium oxide weighs. So let me make myself a little space here. Magnesium oxide. And we have to find what number goes in here. So for this, we can't just look up magnesium oxide on the periodic table. We have to find its components and add them together. So we know magnesium oxide is made out of 1 magnesium and 1 oxygen. So we have to go to the periodic table and find out that magnesium's molar mass is this, and oxygen's is this, 9994. And then you're going to add those together, and you're going to get an answer for what a mole of magnesium oxide weighs. So I think we concluded that it was 40.304 or something like that. So that's going to go down here, 40.304. And then you're going to do out your math, and you're going to get something in grams. And I think we settled on 3.14, something close to pi, actually. So what you're looking at here is you've now figured out, based on what you put in, so you put in 1.89 grams of magnesium. You couldn't use this machine on grams. This machine only accepts moles or some other number of molecules or atoms. So you had to get a number of things you were putting in. You used your 1-to-1 ratio to dictate that you had to get this many moles out of the product, which is magnesium oxide, and then you had to convert it into grams. So it's multi-step. So I think of the whole process as this box, so this is the machine you want to use, and you have to have the right kind of thing to put into it. So if you have grams, they're not going to go into that machine. The machine doesn't take grams. So you got to convert it first into the right thing that goes into the machine. The machine will give you an answer in a number of things, like in moles. And so then you have to take those moles and convert that into grams. So then you're finally going to get this answer that's like, okay, if I put in 1.89 grams of magnesium over here, that's going to give me 3.14 grams of magnesium oxide in the end. And that right there, when you're looking at how to do your lab, is what we call the theoretical weight of magnesium oxide. It's the theoretical weight because it's what, if your experiment had gone perfectly, in theory, you should have gotten 3.14 grams of magnesium oxide. You may not have gotten that because in every experiment there's the possibility for error, little things go wrong, you don't do something quite right. So what your job is to figure out what did you actually get in the lab. So you put your magnesium oxide on a scale and you got a number of grams, and you're going to compare that to whatever number you get in this box for your experiment. So your theoretical weight of magnesium oxide is how many grams you should have gotten based on what you put into it. And then your calculated or your observed mass of magnesium oxide is what you actually got. When you put that thing on the scale, how much did that pile of ash at the end of the experiment actually weigh? So this whole concept is what we call stoichiometry. It's why we use moles. The reason we need moles is because we can't put grams into this machine. This machine does not accept grams. So even though this reaction is super powerful and can predict what's going to come out at the end of your experiment, it can only make that prediction in numbers of things. It can't help you if all you give it is grams. So for any of these problems, you got to figure out, where are you in this box? Are you starting with grams or are you starting with moles? And you have to remember that it's kind of a big box. You can't go directly from grams to grams. So if you're asked, if you're given grams and you need grams as an answer, you're going to have to run it through this box first, come all the way down, and end up over here. So think of it as a big box. We'll do lots more examples of it, and it's all just going to be great.